use of Nernst equation to find EMF. So when electrodes are given, so here we have two systems. The first one is platinum electrode and Sn2 plus Sn4 plus system. So whether it is anode or cathode, irrespective of that, what we will do, we will always write the equation in terms of reduction. So it will be Sn4 plus 2 electron is converted to Sn2 plus. So always write the reaction when it is only the half reaction in terms of reduction. So that is why Sn4 plus is written first. It is accepting 2 electron and it is reduced to Sn2 plus. So in this way we have to write the equation. So the Nernst equation will be, so this is the EMF of the cell, then E0, that is the standard reduction potential of the cell. So standard reduction potential, it is basically E0 of Sn4 plus and Sn2 plus, which is also written here. Okay. Now this value, if it is given, we can calculate it. Then minus 0.0592. Here N value will be 2 because 2 electron involved. Then log 10. In the numerator there is product concentration, in the denominator there is reactant concentration. So here product is, obviously we have to write that term which is present in the right hand side, that is product side. So that is why concentration of Sn2 plus, that is in the numerator, and concentration of Sn4 plus, that is in the denominator. So if the concentration values are given, then the full calculation that is possible. Fine. Now for the second one, here we don't have to use any inert electrode because aluminium is solid, so aluminium itself can be the electrode. Again, the reaction should be written as Al3 plus accepting 3 electron and it is converted to aluminium. So we have not written it as aluminium is oxidized to Al3 plus. No, it is the reduction reaction. In that format we have to write. So now if the value of E0 of Al3 plus and Al, if it is given, we can put it in the Nernst equation. So E cell or E electric or equal to E0 electric minus 0.059, sometimes it is written 0.592, that is not important, then divided by N. So N is here 3. Now again product is written first, then reactant. Now in the product side we have solid aluminium, so its activity will be considered, that is concentration will be considered as 1. So that is why here in products, that is in the numerator, in case of product concentration, it is written 1. And in the denominator, this is the concentration of aluminium 3 plus. Now if we bring aluminium 3 plus for denominator to numerator, then this sign of, that is negative sign, that will be converted to positive sign, because now when we are bringing it, we are writing it as log Al3 plus, then it will be, its power will be minus 1. So that power, if it comes before log, then minus will be positive. So ultimately this is the expression for Nernst equation. If these values are known, we can put it and we can get the E cell of the system. Okay. Another two system. Here we have, when electrodes are given, sorry, it is 2 times. So here electrodes are given, so we will write the reduction reaction first. AgCl, if it accepts 1 electron, it will be converted to, now in AgCl there is Ag plus and Cl minus. Now the Ag plus, that is the cation, if it accepts this single electron, it will be converted to solid Ag, and Cl minus, that will be as it is. So in the product side, what we have? We have Ag0 neutral, and that is metallic silver and chloride, and in the left hand side we have silver chloride and electron. So now the Nernst equation, remember it is, that is the concentration of AgCl, it will be considered as 1, concentration of Ag, that will also be considered as 1. Only the concentration of Cl minus will be there. So the Nernst equation here, for this system there is a specific value for the standard reduction potential, which is for AgCl Cl minus system. So this is AgCl Cl minus system, and here n value is 1, only one electron involved. So in place of n, 1 is written. And product side there is only Cl minus because this is 1, and in the reactant there is only AgCl, so this will also be 1. So finally the expression will be like this. The next equation, here Cl minus Cl2, then Pt. So again we will write it in the form of reduction. So chlorine half, if it accepts 1 electron, it will be converted to chloride. Now here concentration, partial pressure of chlorine, because it is gaseous, in gaseous state. So obviously partial pressure will be considered. That is given 1 atmosphere. So in the product side we have Cl minus. Its concentration is not given, but it may be given, and in the denominator there will be pressure of chlorine gas, which is given 1 atmosphere. So here the equation will be first E cell, then equal to E naught cell minus 0.059 by n. So here n value will be 1. Now if you have written the reaction in this form, suppose you have written it as 2 electron then 2 Cl minus. In that case you have to write electron as 2. But you will see that when you will put in the product concentration Cl minus, its power will be 2. That is, there will be a power 2. Okay, like this. So this power, it will come before log, and this n is 2 and the power 2, that 2 will be cancelled. So ultimately, whether you write the equation in this way or in this way, it is that doesn't matter anything, because ultimately it will take the same form. So put, it is the E naught cell, which is for chlorine chloride system. N value is 1 because we have written the reaction in this form, half chlorine plus electron. And in the product side there is concentration of Cl minus. In the reactant, this is the concentration of chlorine to the power half, because here coefficient is half, but it will be ultimately the pressure of chlorine, which is mentioned 1, so it is 1 to the power half. Now 1 to the power half is simply 1, so it is actually 1, and ultimately the reaction will be reduced to E's chlorine chloride system equal to E naught chlorine chloride system minus 0.059 by 1 and log chloride ion concentration. So in this way we can use Nernst equation to find the EMF of the cell, provided the concentration of the product and reactant given, and also the standard electrode potential that is also given. Okay, here we have a problem. Here E naught value for two systems are given. One is for Fe3 plus to iron, that means Fe3 plus accepting 3 electron and it is converted to iron. Another E naught is given, which is Fe2 plus 2 iron, that is accepting 2 electron and reduced to Fe. So this is for the first system, this is for the second system respectively. So we have to find the E naught of Fe3 plus Fe2 plus. So for your convenience you can also write it in this way, that Fe3 plus to Fe2 plus then Fe. So this value is given, which is minus 0.036. This one is also given, which is minus 0.44, but we have to find this. Okay, now you can do the calculation from this diagram, or else there is another way you can do it, though in similar type of problem I have also discussed, where I have shown that in both ways you can do it. Okay, it is up to you which one will be more convenient. So the two equations we will write first. This is the first equation accepting 3 electrons, and the second equation accepting 2 electrons. So here we are getting del G naught 1, which is equal to NFE. We know that del G naught is equal to minus NFE. So for the first reaction, we are considering it is equation number 1. So that is why del G1. N here is 3 and E naught of Fe3 plus Fe system. For the second equation, it is del G naught 2. Now the number of electrons involved is 2. So N is 2 and it is minus 2F E naught of Fe2 plus Fe. Now if this is the second equation, now deduct equation 2 from equation 1. So what we will get? 3 electron minus 2 electron. There will be negative sign. So now we are getting only 1 electron and these two will be cancelled. Fe2 plus will be at the right hand side. So we have to arrange the two given equation in such a way so that we can get the equation for which we have to find out the E naught value. Okay. So as we have done equation 1 minus equation 2, so that is why del G naught, that is del G naught means del G naught that we have to find. You can also write it as del G naught 3. So we will put all the values in place of del G1 naught and del G naught 2 and we can get the value of del G naught. Now here number of electron involved is only 1. So N value will be 1. So the next calculation will be, in the left hand side we will write minus F because here N is 1, here N is 3, here N is 2. Now this negative sign and the negative sign of 2F E naught, that will be cancelled, so it will be ultimately positive. You can also take that is negative sign can be taken common, and finally F will be cancelled from both sides. So we are left with 3 into this reduction potential value of Fe3 plus Fe system minus 2 into reduction potential value of Fe2 plus Fe system. Okay. Now from this diagram involved, that is 3 electron involved. So here we will multiply it with 3 and this will be multiplied by 2. Okay. Now this total value is given. So obviously from this quantity we have to subtract minus 0.44 into 2. So from the diagram also you can do the same calculation. Okay. But you have to be careful that for the system for which we are actually trying to calculate the value, how many electrons are involved. So here it is only 1 electron. So that is why when we are deducting minus 0.036 into 3, then minus of minus, that is ultimately it will be plus 0.44 into 2. Then don't forget to divide it by 1. Here it is 1, that is why it is fine, but it may be 2 or 3 or any other value. Okay. So it is up to you whether you want to do the calculation directly from this diagram or by taking this or taking the help of this equation, that is del G naught is equal to NF E naught. So finally what value we are getting? This negative will be cancelled, so it will be plus. So this quantity is lesser, this quantity is larger, so that is why finally the value is positive, that is 0.77. So correct option will be first option. Okay. Next problem. Which of the following graph? Here we have total 4 graphs given in options A, B, C, D. So this graph is E cell versus log Zn2 plus Cu2 plus. Correctly correlates E cell as a function of concentration of ions for the given reaction. So which graph will be correct for this equation? It is given, and E cell of this system, that is also given. Okay. Now for this reaction, that is Zns plus Cu2 plus, this is solid, this is that is some concentration is there because M, that is molarity, this is M prime. So Cu2 plus is reduced to Cu and Zn is oxidized to Zn2 plus. So for this reaction, if we write the Nernst equation, it will be E cell equal to E naught cell. E naught cell will be this value, okay, 0.059 divided by N. So number of electrons involved, you can easily understand from this equation, it is 2, okay. And if you are having trouble that whether what is the N value of N, then you can write the 2 half cell individually, and from that is when you are adding these two equations, electrons will be cancelled. So put that number of electrons which you have cancelled. So here it is 2. Then log of product concentration. Now what we have in the product side, we have only Zn2 plus, because this is its concentration is 1. Similarly in the left hand side, that is in the reactant side, this is having 1 concentration, so only Cu2 plus will be in the denominator. So log Zn2 plus concentration divided by Cu2 plus concentration, okay. Now this value is 1.10. We will compare this equation with y equal to mx plus c, which is the equation of straight line with intercept. So here m is slope, c is intercept, and what is our y? Y is E cell, because it is E cell versus log Zn2 plus U2 plus. So this is y, this is x. So in the left hand side we have y, fine, and x is this quantity. So whatever is written before x, that will be considered as m. So this part is basically m, right? So m is minus 0.059 divided by 2, and c is 1.10. Okay. Now if you look at the options, the first option here, the slope is positive, okay. So slope positive and negative, how we will understand? Here you can see that y versus x, if m is negative, that means when the value of y will increase, x will decrease, because there is a negative sign. So in that type of relation, we say that slope is negative. But if it is proportional, that is when x is increasing, y is also increasing, in that case it will be positive slope. So this is positive slope. So this is not correct option. Okay, and here also intercept is 1.1, because it is cutting at the y-axis at the value 1.10. So here this is not correct option, though intercept is fine, but slope is positive. But in the equation that we have compared here with this straight line equation, we have obtained slope negative. This is negative. Now come to the option B. Here intercept is again 1.105 and here slope is negative. So see, as we are increasing the value of x-axis, then the value of y is decreasing, because if you draw a line here, if this is the value of y, now when you are drawing another line from this increased x value, now the y that you are getting, this is lesser. That means slope is negative. So this is actually the correct option. Now why not C and D? In C, this is a straight line. Though it is cutting it here, but as it is straight line, that is, sorry, not straight line, I mean to say it is parallel to x-axis. So that means that with change in the value of x, there is no change in the value of E cell. That is, with change in concentration of Zn2 plus U2 plus, there is no effect on E cell. But that is not correct. Okay. So that is why this is wrong option. And in the last option, here as we are increasing the value of x, suppose you are moving from left hand side to right hand side, what we are seeing here, the value of E cell, first it is decreased and then it is touching at 1.1 and then again increased. But that is not the case. which is clear from this equation. So that is why correct option will be option B. Okay. So here the main thing is we have to compare the Nernst equation with the equation of straight line. And remember, if here from the graph it is clear that intercept is there, so that is why we have also written C. But if it is going through origin, then it will be y equal to mx. But if you carefully look at the Nernst equation, you will see there is actually y, x and also extra term which is free of x. So it must be the intercept. So that is why you have to consider the equation of straight line which is involving the intercept, y equal to mx plus c, not y equal to mx. Okay. Now we have to know, we have to learn one particular term which is known as temperature coefficient. Okay, so this temperature coefficient, this term we can, that is, it is equal to actually what? That we can get from Gibbs-Helmholtz equation. Now Gibbs-Helmholtz equation is basically from thermodynamics we can get. Okay, so another equation here, del G is equal to del H minus T del S, which is very common equation. And the left hand side, the equation that you are seeing, that is the Gibbs-Helmholtz equation. So what we will do, we will compare these two equations and we will try to find out what is temperature coefficient. Okay, so basically temperature coefficient is del E divided by del T at constant pressure. That means change in the electrode potential with change in temperature. That is the effect of increasing temperature on the value of electrode potential. That is the temperature coefficient. Okay. Now why this term is important? Because sometimes you can get numericals which is involving this temperature coefficient. Suppose it is asking find the value of temperature coefficient. Then how to calculate the value of this? And also sometimes it may be that temperature coefficient value is given. That is the value of this term is given. And you have to find del H or del G or del S. Okay. So from this equation, we can also write it as del G equal to del H plus T del G del T P. Suppose this is equation 1. This is equation 2. Now compare these two equations. Left hand side, in both cases we have del G, then we have del H, then we have minus T into del S, and here what we have? Plus T into this total term. So comparing these two, now we can write that del S is actually equal to T del G del T at constant pressure. Okay. Now we will put del G equal to minus NFE. Sorry, there will be negative sign. So if it is so, now in place of del G we will write minus NFE. So the minus and this minus, it will be cancelled. So ultimately what we will get? Del NFE by del T. Now N and F, these two are constant, so it will come out of this derivative. So it will be N F T del E del T P. So basically find what we are getting. Sorry, it is not T. T should not be written because when we are comparing in both equation there is T. So del S is simply equal to this. This is equal to del S. So finally we can write that del S by NF, that is equal to temperature coefficient. So if entropy value is given, N and F, this can be easily known. F value is, there is a particular constant 96500, and if left hand side quantities are given, you can find out temperature coefficient. So this is temperature coefficient, and if temperature coefficient is given, you can find del S. Okay, and in this from this equation, if you know the value of del S, value of del H, you can find value of del G. Or suppose if it is given the value of del G and del S, then we can also find del H. Okay, so this is the utility or application of temperature coefficient. So now we will see a problem which is this related to this temperature coefficient. So what is mentioned here? The standard electrode potential E naught and its temperature coefficient. See, this is the value. Constant pressure is not mentioned, but del E naught by del T, that is temperature coefficient for a cell is 2V and this quantity. So this is actually the temperature coefficient and this is E naught respectively at 300 Kelvin temperature. So E naught value is given, temperature coefficient that is also given. See, what is the unit? Volt per Kelvin. It has to be because the numerator term is volt, this is Kelvin, so it must be volt per Kelvin. And the cell reaction is given, so this reaction you have seen several times, this is very common. The standard reaction enthalpy del R H naught of the equation at 300 Kelvin in kilojoule per mole unit we have to find out. That is the question. So as we have seen in the last slide that if other quantities are known, that is temperature coefficient or del G, then we can easily find out the unknown quantity. R value is given, so always use that value which is given here, then only you will get, you can match with the options, because this R it sometimes written as 8.314, but here it is written simply 8 joule per Kelvin. And F value is also sometimes you can find that it is 96500, but here it is 96,000 coulomb per mole. Okay, so always use that values of the constants that is given in the question. Okay, so this equation we know del G naught is related to enthalpy and entropy by this equation. Now we will write T del S with del G, so del G naught plus T del S. Now del G naught is equal to minus NF E naught. So in place of del G naught we can put this value, and del S is equal to, remember in the last slide what we have done, del S by NF, that is equal to temperature coefficient, or when it is simply del S we can write it is NF into del E del T at constant. So after writing this, what you can do, just keep it in this way, because here del E naught del T value is given, you know what is the value of N, E naught is also given and F is also known. Okay, so we can take common this minus NF E naught, right? So if we take common minus NF, then inside there will be E naught minus T E naught dt. Now N value is 2, F is 96000, E naught is 2 volt minus T is 300 Kelvin. There is a negative sign in temperature coefficient, so it will be positive. So 300 into 5 into 10 to the power minus 4. Okay. So this temperature unit will be cancelled. Ultimately the unit of this quantity, it is volt. This is also volt. Is minus 192,000. This is 0.15. So ultimately the value will be 412,800. Okay, so here it will be in joule unit. So finally if we convert it to kilojoule, because it is mentioned that there is the options that you are seeing here, all should be in kilojoule per mole. Standard reaction enthalpy del R H naught at 300 Kelvin in kilojoule per mole unit we have to find. So it will be 412.8 kilojoule per mole. Okay, so here the unit is C and here the unit is V. Okay, so we know that joule, that is charge into volt. Okay, so finally it is converted to the unit joule. So it is matching with which option? It is matching with first option. It is a negative sign. Okay, volt into coulomb, that will be joule. Next problem. Standard oxidation potential of nickel 2 plus electrode is given. See, if you want to know the reduction potential, simply put a negative sign. Okay. This is combined with a hydrogen electrode in acid solution. So the question is, at what pH of the solution will the measured EMF be 0? At 25 degrees centigrade. Concentration of nickel 2 plus given 1 molar and partial pressure of hydrogen, that is also given 1 atmosphere. So as oxidation potential is given, so here we can consider that nickel 2 plus, that is the oxidation reaction is actually going on. So if this is the oxidation reaction, that means this reaction will take place at anode. So at anode the reaction will be nickel converted to nickel 2 plus 2 electron, and cathode reaction is She. And you can also easily compare that why it is for anode, because if it is reduction potential, then it is minus 0.236, and we know that E naught of the combined cell, it will be E naught of cathode, that is the right hand side, minus E naught of anode. So E naught of cathode is 0 and E naught of anode is, that is mostly what we do when oxidation potential is not mentioned, we simply take the two reduction potentials values of the two system, oxidation system, reduction system, and we use this equation. So it will be 0 minus 0.236. So ultimately it is positive 0.236. But as here directly the oxidation potential is given, that means for this, that is nickel is oxidized to nickel 2 plus, the corresponding E naught value, it is better you write E oxidation of nickel 2 plus. So this value is given 0.236, and at cathode reduction reaction is going on, so it will be H plus 2 accepting 2 electron converted to H2. So this value is, that is E naught reduction, this is we know it is 0.0 volt. So as directly the oxidation potential given, so don't do the what you should not do, don't subtract 0.236.0, directly add these two. Okay, so finally if you are adding these two equations, you will get nickel 2H plus, electron cancelled, in the right hand side hydrogen and nickel 2 plus, and E naught of this cell will be simply at these two value, which is nothing but 0.236. Now we will write the Nernst equation. So the Nernst equation will be E cell, E naught cell minus 0.059 divided by 2, then log concentration of the product side. In the product side we have nickel 2 plus and H2, nickel 2 plus concentration and partial pressure of H2. which is basically 1. And in the reactant side, we have only H plus, because this is, it will be considered 1. H plus to the power 2. Okay, so now put the values. Now here, see, if this is combined with a hydrogen electron acid solution, at what pH of the solution the measured EMF will be 0. That means if this is 0, under that condition, what is the pH? So now we can write it as E naught cell, which is basically 0.236, that is equal to 0.059 by 2 log, these two are 1, this is 1, this is also. So it will be H plus. Now this power 2, that we will bring here. And as we have written this denominator term in the numerator, so there will be a negative sign. These two are cancelled. So it is minus 0.059 multiplied by pH, because negative log of H plus, that is pH. pH is negative logarithm of H plus concentration. Okay, so this negative sign we will consider when we will write pH is equal to minus log H plus. So this negative sign will be ultimately positive. So this is the pH, and E naught cell is 0.236. So 0.236 equal to 0.059 into pH. So pH is basically 0.236 divided by 0.05. And if you do it, you will find pH is 4. So this is the answer. It is actually integer type of problem. Okay. So in this way we can find out by taking the help of Nernst equation what will be the pH of this cell. That is when the measured EMF is 0. That means E cell will be 0. And be very careful whether oxidation potential is given or reduction potential is given. If nothing is mentioned, you can simply take it as it is reduction potential, because that is the IUPAC convention. But if it is specifically mentioned oxidation potential, then that is why we have not done E naught of cathode minus E naught of anode. We have directly taken this value. Okay, because oxidation potential is given. Next problem. Standard reduction potential for Ag plus Ag electrode 25 degrees centigrade 0.799 volt. It is almost 0.8. And what are other information given? Ksp of silver iodide, that is given 8.7 10 to the power minus 10. It is power 10 to the power minus 17. So we have to evaluate the potential of Ag plus Ag electrode in a saturated solution of AgI. So see, try to understand. Here standard reduction potential of this system is given. But we have to find out the value of standard, not standard reduction potential, because whenever we are saying standard means it is at a particular value, which we can find from electrochemical things. But now we have to find out the reduction potential of the same system, but in the condition provided is, now it is present in saturated solution of AgI. So the saturated solution of AgI, if you know the corresponding concentration of Ag plus in AgI, which can be easily find out from Ksp, then in place of concentration of Ag plus, you have to put this value. Okay, so this is the first part. Two questions are there. In the first part, it is asking you have to find out the reduction potential of Ag plus Ag system in a saturated solution of Ag. This is the first part. And the second part is also calculate the standard reduction potential of I minus AgI Ag electrode. So this electrode you can obtain if you combine Ag plus Ag electrode and AgI I minus electrode. Okay, so first we will solve this part and then the second part. In the first part, before going to first part, we will find out Ag plus concentration. So Ksp is equal to Ag plus Cl minus. Now Ag plus and Cl minus, these two are, it is 1:1. So you can write it as Ag plus square. Okay, so Ag plus will be root of Ksp. Now Ksp is 8.7 10 to the power minus 17, but I will write it as 87 into 10 to the power minus 18, because if it is a even number, the root calculation it will be easier. So root 87, this is 9.33, 10 to the power minus 9. So now we know what is the value of Ag plus. So see, this is the first part. Now for the reaction Ag plus E Ag. So when we are doing this only for this half reaction, that is Ag plus electron Ag. So as it is half reaction, write it in the format of reduction. Now use the Nernst equation. 0.59 by 1 log of product side we have silver, so its concentration is 1 by concentration of Ag plus. So in this Ag plus concentration we will put this value, and E naught cell is already given 0.799. So minus 59 log 9.33 into 10 to the power minus 9. Now as we have written it in numerator, because we are bringing it to upper side, so this negative sign will be now positive. Now you can write it as log 9.33 minus log that is 10 to the power 9, that means minus 9 log 10, and log 10 is 1, so it is simply minus 9. So after the full calculation you will see that the value that we will obtain is 0.325. So see, standard reduction potential is almost 0.8, but when it is present in saturated solution of AgI, now it is reduced to 0.325. Okay, so this is the first part. Now we will do the second part. Second part is this one. So for the second part, first of all we have to write the combined equation, that is this one. So one equation we have already written here. Okay, and another equation is, so let me write it again, Ag plus electron to Ag. Another equation is AgI accepting electron. This is actually the reaction which is at cathode. This is converted to, now AgI means what? Ag plus I minus. Ag plus will accept electron, it will be converted to metallic silver plus I minus. Okay, so as this is the reaction at, which is actually the reaction which is going on at cathode. So this second equation, and if it is first equation, what we will do, we will subtract 1 from 2, because this is the reaction which is going on at anode, so that is why it will be subtracted. So electron will be cancelled, AgI will be in the left hand side, silver will be cancelled. And in the right hand side, there will be Ag plus and I minus. Okay, so combining these two, basically we are getting this equation. Okay, now we will write the Nernst equation. Minus only one electron. In the product side, we have Ag plus and I minus. And in the reactant side, it is simply AgI, so it will be having concentration 1. Fine. Now see, this portion, this is nothing but KSP. So you can put the value of KSP 8.7 10 to the minus 17. And as we are trying to find out the value of E naught cell, okay, so we have to consider this E cell as 0. That means it is now at equilibrium. So under that condition, if it is 0, now E cell will be log of 0.7 to the power minus 70. So after calculation, it will be log 8.7 minus 70. So ultimately, as this is negative, then 17, it will be ultimately negative, and the value is minus 0.95. Okay. Now the important thing is, for this first equation, we know what is the value of standard reduction potential. It is 0.799. And we also know that for the combined reaction, suppose this is equation 3. For the combined reaction, what is the value of E naught cell? Which is minus 0.95 volt. So use this equation, that is E naught cell is equal to E naught of cathode minus E naught of anode. So here you know E naught of cell of the reaction, which is minus 0.95. And you also know what is the value of that is E naught A. So this E naught C we can write as E naught of I minus AgI Ag. Basically this one, minus E naught of Ag plus Ag. So this value we have to find out. Okay. So it will be, and this one is 0.799. So ultimately it will be, that is E naught of I minus AgI Ag, that will be minus 0.95 plus E naught of Ag plus Ag, which is 0.799. Okay, so it will be minus 1.51 volt. So the second, it is the first answer, and the second answer is, that is also calculate, this part is minus 1.51. Sorry, I have made a mistake. It is not minus 1 point, it is minus 0. 0.151. Minus 0.151. This is the answer of the second part. And the first part is 0.325. Okay. It is also clear because it is minus 0.95 and this is almost 0.8. So it will be minus 0.1 something. Okay. So it is 0.151 volt. Another problem, the magnitude of the change in oxidation power of MnO4 minus Mn2 plus couple, and that is x into 10 to the power minus 4. Here don't be confused between these two signs. It is actually s into x into 10 to the power minus 4 volt. So this is the magnitude of change in oxidizing power of this system. Now it seems as if what is oxidation power, but it is nothing but the value of reduction potential of this system when there is two different conditions, because we have to find out change in oxidizing power. That means basically we have to find out the reduction potential of this system at two different conditions. One condition is H plus concentration is 1 molar, another condition is H plus concentration 10 to the power minus 4 molar. So if the H plus concentration is decreased from 1 molar value to 10 to the power minus 4 molar. So when acidity is decreased, then what is the change in the reduction potential value of this system? That is actually the oxidizing power. Here some more information. Assume concentration of MnO4 minus and Mn2 plus to be same when you are changing the H plus concentration. And the value of x we have to find. Okay, so whatever will be the final result, you have to write it in this format. Then compare what is the value of x. And this is 0.059, that is known. So for the first part, okay, let me write the equation. MnO4 minus, and remember this is in acidic medium. MnO4 minus, here oxidation state is +7. It is reduced to Mn2 plus. Now when it is reduced to Mn2 plus, then we will balance the oxygen number, because left hand side we have 4 oxygen atoms. So we will write here 4H2. Now when we are writing 4H2O, basically you are adding 8 hydrogen atom. So to balance it, we will write here 8H plus, and you can do it in terms of H plus because it is in acidic medium. Okay. Next thing what we will do, in the left hand side, if you consider the charge, there is 1 negative charge and 8 positive charge. That means it is 7 positive charge. But in the right hand side, you have only 2 positive charge. So you have to make it both sides same. So that is why we will add here 5 electrons, so that this 7 positive charge, now it is converted to 2 positive charge. So now both sides will be equal. So this is the equation for which you have to write the Nernst equation at two different conditions. In one condition, H plus concentration we have to write 1 molar. Another condition we have to write 10 to the power minus 4 molar. And in both cases, these two terms, their concentration will be unchanged, because that is already mentioned here. So the first condition, when H plus concentration is 1 molar, under that condition the Nernst equation will be, that is, if we put the value of H plus is 1 molar, this is the common Nernst equation that we will use in the both cases. E naught cell minus 0.059, total number of electrons involved 5. So see, this is not a redox reaction, it is only one system. Okay, that is as if it is half reaction. And in the product side we have Mn2 plus and H2O, so only this will be considered. And in the reactant side there is H plus to the power 8, which is written here, and concentration of MnO4 minus. So when it is 1 molar, simply it will be 1. So ultimately the equation is reduced to in this form, and this is E1 because this is for the first part. And for the second part, when H plus is 10 to the power minus 4 molar. So if you put in this equation 10 to the power minus 4, so it will be something like this. Next, what we are doing, this log, this particular portion, just focus, log Mn2 plus MnO4, this is one term, and 0.059, that is multiplied with this term one time and with this term another time. So when there is into sign, that means it will be, let me write it here, suppose you have log A into B, then you can write it as log A plus log B. And if this is A by B, then it will be log A minus log B. So this is A and this is B. So first it is written log A multiplied by this common quantity and then plus. Why it is plus? Because this is actually in the denominator 10 to the power minus 32. But if you are bringing it in the numerator, there will be a negative sign, and this negative sign and this negative sign will be cancelled. So ultimately it is positive. Okay. So this is E2. Next, what we will do? We will take the difference between these two, and it is simply the mod value. Okay. Negative sign, even if it is there, that we don't have to consider because we just want to know what is the magnitude of the change in oxidation power. See, that is why it is important to read the question very carefully, because if you are writing the value of X in negative, it will be wrong. Okay, so E1 minus E2. So this is first equation, this is second equation. So subtract second equation from first equation. So E0 will be cancelled. Then this term and this term, these two are actually same. These also will be cancelled. So ultimately what will be remaining? This particular part will be remaining with a negative sign, but as we are taking mod value, it will be like this. So it is 0.3776, but we have to write it in this format because we have to compare it with X into 10 to the power minus 4. So that is why we have written it in this format. And now compare, X value is 3776. Okay. Conductance. So what is conductance? It is the property of the conductor. Now conductor may be metallic in nature or it may be electrolytic in nature. And this property facilitates the flow of electricity through the conductor. That property is actually conductance, or sometimes it is also called conduction. It is equal to reciprocal of resistance. Now resistance, when we are saying, you can easily understand that this will oppose the flow of electricity. So that is why conductance will be reverse of resistance. So you can now say that it is 1 by R. R is for resistance, and the unit of resistance is ohm. Unit of R is ohm, which is written in this way. So obviously the unit of conductance will be ohm inverse. Fine. Now conductor, this is conductance, that is a property will be called conductance. But if it is conductor, that means it is any material that will allow the electric current to pass through it. And if it is not allowing, then that particular material will be called insulator. So here we have this system. Here we have taken steel paper clip. So this is metal. This will act as conductor. So obviously there will be current. So that is why bulb, it is glowing. Fine. But suppose you have taken any insulator. So here it is a plastic toy. So as it is insulator, the bulb will not glow. Okay, because it cannot, it will not facilitate the flow of electricity. It will oppose it. Okay. Here we have some examples of conductor. So this side is conductor, this side is insulator. So ceramic bowl, steel nails and screws, mostly we'll see that the metallic things that are conductor. Sorry, I should not write it here because here it is all are mixed. So here we have ceramic bowl, plastic toy. So this is metallic, this is metal. So this will be conductor. This is insulator, insulator. This is insulator. This is also, so this is conductor, right? This is insulator, conductor, conductor. So different examples we have here. So mostly when it is you will see any metal, obviously it will be conductor, and there may be some electrolyte which also can act as conductor, but here we do not have any examples of electrolyte. All the conductor that you are seeing in this table all are basically metal. Fine. So we will go into the details. Fine.